In our last lecture, we talked about the magnetic moment of the electron and how that can induce fine structure in atoms. Well, we can move on now to talk about hyperfine structure, which is yet another form, and that relies on considering that the nucleus can also have a magnetic moment. So let's develop that a little bit and see how that plays out. So remember that the nucleus has a magnetic moment. And the most obvious and straightforward case of considering the effect of the nucleon magnetic moment is to consider just the magnetic moment of a proton and the hydrogen atom. So we'll use that to develop the case of hyperfine splitting and its particular application to the 21 centimeter line of hydrogen, which is essential to understanding the universe around us. So consider the nucleus magnetic moment. So for hydrogen, we want to consider just the magnetic moment of the proton. And that is given very similarly to the magnetic moment of the electron. It's given by a Landé G factor, which is the proton Landé G factor, times E times H bar, times 2 times the mass of the proton, times the speed of light, times I, which is the nuclear spin. And that's equal to 1/2 for a proton, just like it is for an electron. But of course, the magnetic moment of this is inversely proportional to the mass of the proton. And so therefore, the magnetic moment for a proton is much smaller than the magnetic moment for an electron because the electron has much less mass than the proton. And the Landé G factor for a proton is about 5.585, so that doesn't contribute much, but we find that the magnetic moment of a proton is on the order of 10 to the minus 3 to 4, the magnetic moment for the electron. So it's a much smaller effect that is going to take place here. But nonetheless, it is an effect. So for this nucleus, we can consider what the magnetic field of the nucleus is. And in this case, we're just dealing with the simple situation of the spin of the proton, and that's given by 3 r hat times r hat minus dot mu, minus mu, which is the magnetic moment, over the radius cubed. Now this first term goes to 0 for spherically symmetric states. And that means that for the S state, B of r is very simply the magnetic moment of the proton over the radius cubed for S states. So here we're dealing with, of course, the S state of hydrogen. That's the ground state of the hydrogen atom, and it induces a magnetic field, which is related to the magnetic moment of the proton over r cubed. And this results in a change of energy level, which is once again just related to, in this case, how the electron spin magnetic moment interacts with this magnetic field, or in that case, how we can say that the proton magnetic moment dotted with the electron magnetic moment over A naught cubed, where A naught is the Bohr radius, and it's just m e squared. So we can write that out as E h bar squared over the mass of the electron times the mass of the proton times the Landé G factors over c squared. And it's the spin of the proton, which is I, times the spin of the electron, which is S, or dotted with S, I should say, over A naught cubed. And so now we have to define an additional total angular momentum, so that this really is the total angular momentum now. And it's given by L plus S plus I, which relates to the spin of the proton now. And in our situation where we're dealing with the S state, then L is 0. And so F just becomes S plus I. And that means that for hydrogen, it can be equal to F of 0 or F of 1 in its ground state. And we can work through, just like we did for the situation of fine structure, where we broke this up into various different terms, where we had, and in our case, we had an L times an L plus 1 and an S and times an S plus 1, but we can do the same thing for our total angular momentum now. And these are just the numbers where I is going to be the proton spin, the electron spin, plus 2 times I dot S. And we can substitute that in to work out that the energy difference is on the order of EH bar squared, with the mass of the electron, mass of the proton, C squared times 1/2 F times F plus 1 minus 3/2 in the hydrogen example, A naught cubed, pardon me, that should be a cube. And for hydrogen in its ground state, we have that the difference in energy over the n equals 1 energy is very simply mass electron over the magnetic moment of the electron. And that comes out to producing an energy difference that is equivalent to a frequency of 1420 megahertz. And that is the hyperfine structure of hydrogen, otherwise known as the 21 centimeter line. And it turns out that's a very important line, because hydrogen is the dominant atom in the universe. And although it's a very small energy shift, and it's very, very small A factor, Einstein A factor, we actually see an enormous amount of atomic hydrogen. And we'll develop that up in next week's lectures.